12.5 arc length and curvature. The arc length formula is very similar from what you've seen throughout your calculus career. Here, capital C is a smooth curve. It's always given by some kind of position or path vector, R of t. And so, and they're defined on some interval, some closed interval from A to B. So the arc length is the interval of basically the change of rate for the velocity. As the curve moves along the path, the derivatives form some kind of pattern, and if we take the rate of that as that changes with respect to the interval, we get just the measure of the length of the arc of the curve from some value from A to the end point of the interval from A to B. I want to spend more time on the curvature. I think the arc length has been well established in the past. Curvature is simply the measure of how sharply a curve bends. The definition, let C be a smooth curve in a plane or space region given by R of S, where S is the arc length parameter. Then the curvature, denoted by capital K, is given as the magnitude of the rate of change of the tangent vector with respect to the rate with respect to the arc length itself, ds. And as you can see, the illustration for this so-called the bending, the measure of the bending, which we get the curvature. Some helpful formulas that we'll need to calculate the arc length. Typically I use this first one, that the curvature is the norm of t prime divided by the norm of r prime. However, I've found at times it helpful to use this ulterior formula for the curvature, that curvature is the dot product of the acceleration and the normal vector divided by the velocity, the norm of the velocity vector to be squared. So the norm, excuse me, is not a vector, so the velocity is given as a vector. We take the norm of that and then we square it. So you get a number. And that's what the curvature is. Let's look at some problems now.